I'm Dr. T and welcome to my dining room table. So today I would like to talk about stereoisomers. So in this case we have a pair of molecules. They're just kind of some arbitrary things. It's carbon with a bunch of other random atoms around it. And you'll notice how they have 4 different types of atoms around these carbons. And that's actually going to become fairly important because it's going to allow it to do a rather interesting little trick. Now you notice each carbon has a purple, red, yellow, and green ball around it. Well, they look to be the same molecule, don't they? Exactly the same. See, if I overlap them, they overlap completely. Yep, purple on purple, green on green, yellow on red, and red on yellow. Wait, what? Yeah, they don't overlap perfectly because these are very much like mirror images. Just like my hands are mirror images. You know, I have a thumb, 4 fingers, but if I try and overlap them, turtle, they don't overlap. So for this reason, we call these guys enantiomers. They're mirror images of each other, just like our hands are a mirror image of each other. And when we have these carbons that have this ability to have another molecule that's just like it, but in reverse, these carbons, they're called chiral carbons. So if I have something that has 4 things around it, it's possible to have a mirror image of it. Now, of course, we can kick things up a couple of different notches. For starters, I can stick more carbons to this guy. Okay. So now I have 2 chiral centers because this carbon has 4 things attached to it: a carbon, a red, a yellow, and a green, and this one likewise. Okay, let's see if I can orientate these guys in the same way, and I do, and try not to hit the camera. And lo and behold, they're still mirror images of each other. So I have 2 molecules. These guys are enantiomers still. They have 2 chiral carbons. But things get a lot more interesting though once I get 2 chiral centers in here, or 2 carbons that are chiral. And we denote this quite often by writing an asterisk by it. So let's say I modify this just slightly. So now I've affected this chiral center, but not this one. Are they mirror images? Well, not exactly. The bottoms are mirror images, and they're definitely not the same molecule, but they're not a mirror image on the top. They're only partially a mirror image. We call this a diastereoisomer. You're going to have 2 molecules. They're stereoisomers. They're different in the 3D arrangement of bonds, but they're not enantiomers. They're not their own mirror image. And in fact, this guy is an interesting type of diastereoisomer. Notice how I've got this one? Now let me rearrange this guy so he is his enantiomer. I'm going to take this off. I'm going to switch him over. So I'm just making a mirror image. Now, you'll notice they're now mirror images of each other, so they're enantiomers. If I overlap them, yes, they look like they're mirror images. This pairs with that. But look what happens when I do something rather tricky. I'm going to turn this guy upside down. Now, are they mirror images? No, they're the same molecule. Red on the left, yellow on the right. Hey, what happened? Well, this is a special type of diastereoisomer. We call this meso. And this is one where its enantiomer is itself. Essentially what's happening is there's a mirror plane inside of it. So when we think of enantiomers, we think of them being next to a mirror and you're seeing the mirror image. But if you have a plane of symmetry, specifically the plane of symmetry that runs like this, within your molecule, then what you will have is a meso compound, something that is its own mirror image simply by flipping it over and turning it around a bit. Now, why do we care? Well, chemically speaking, they're not going to make much of a difference. If I have one isomer or the other, it doesn't really matter. However, there's a couple of interesting features that, well, it might actually matter just a bit to us. so if I take these guys, I'm going to go back to the original configuration. If I try and make a crystal of these, if I have just this one, it's going to be able to stack nice and rigidly. But if I have this guy, it's not going to be able to stack in the same way that just one enantiomer will have. I'll have a mixture. Now, if you remember back to earlier videos, if I have a mixture and I try and do a melting point, the melting point typically is going to be lower and a bit more spread out when I have a mixture of molecules. In this case, I do. They're very, very similar, but they are slightly different. In fact, if I have a mixture where it is a 50-50 blend of enantiomers, I call this a racemic mixture. Okay, so the melting point gets messed up a bit. That's nice. Why do I care? Well, chemically speaking, once again, they don't do much of a difference. But biological systems are heavily dependent on shape and heavily dependent on the three-dimensional arrangement of atoms. As such, for biological systems, one enantiomer may have one effect, the other enantiomer may have a completely different effect. And there are quite a few cases of pharmaceuticals where one enantiomer is the desired pharmaceutical, the other does literally nothing. Or, even worse, the other one causes damage or is toxic and is a source of certain side effects. So when you have pharmaceuticals, you've got a couple of choices. Back in the old days, the goal was you patent the racemic mixture because it's very easy to make racemic mixtures. And then your patent's about to expire, you patent just the one by itself. This has become frowned upon because this is just gaming the patent system, and it's already gamed enough. Alternatively, what you really need to do is take your mixture and separate it, patent the real thing, and make sure you release this particular enantiomer. And that's generally going to result in a somewhat better pharmaceutical. The other interesting case, of course, is there are molecules like that of licorice and wintergreen, which are both coming from the same basic structure, cavone, but they are enantiomers. So you can get some rather interesting cases that are not necessarily pharmaceutical in origin, but instead, just a little bit more of a different application. So as an organic chemist, if I'm not caring about biological systems, I care a little bit about this, but it's not necessarily a huge deal. But if we're talking biological systems, two different enantiomers, they may as well be completely and absolutely different molecules because they're not going to be recognized by biological systems as being the same. So with that said, have a wonderful day, and I will see you in later videos.